pleasure to introduce now Joshua Chen. So Joshua Chen is an assistant professor at the Colorado State University, and he made postdoctoral research in Costas Maranas group at Pennsylvania State University. His research focuses on the modeling and engineering microbiomes, which have a huge impact on the Earth ecosystem and the life form therein, from global geochemical cycles, soil and planet health to human immune systems. So his group is using genome sequences and multi-omics data to construct systems biological models to understand and predict microbiomes in the terms of their evolution, stability, and biochemical functions under various physical-chemical environments. So thank you, Joshua, and the audience is yours.
Yeah, very great discussion, a lot of interesting ideas, and yeah, I'm happy, I'm honored to have the chance to share some of my work on modeling, microbial communities, and today I'll talk more about the work that I try to based on flux bands analysis that many of you are familiar with, like how to try to model more realistically the microbial community's metabolism. So so first I'll give some very brief introduction to modeling microbial communities. You probably know a lot already, and talk about some of my previous work about incorporation of the steady state composition, and more recently the trying to incorporate the concept of Nash equilibrium. Microbial communities are everywhere, and most of you know that, and you can find them in almost any places that have life, and even extreme environments. And they're very useful. They're like omnipresent and omnipotent. Whatever you want to make, you can ask them to make it for you, or whatever disease you might have is more or less related to some of your microbes, and you can ask them to clean anything for you, and ask them to recycle any waste for you. Almost, that's at least the ideal. And genome scale metabolic models, most of you must have been very familiar with that. So basically, you collect all the metabolic reactions, biochemical reactions identified from genome sequence, and then usually with a biomass composition derived from experimental data or estimated from closely related organisms, then you can predict the growth metabolism based on this flux balance analysis framework, which relies on the steady state assumption of intracellular metabolites and some reaction directionality predicted from sort of thermodynamics there, and delta G, and then also the substrate availability, the medium composition. Then you can, and of course with a biological objective function, which for most of the time we're still limited to using the biomass production. And then we can predict the growth metabolism. It's like based on reaction stoichiometry, reversibility, and biomass composition, and that objective function, then we can predict something. I mean, my opinion on the biomass objective function is like it's not the best, but it's still predicting something. And and in many scenarios we don't really have something that is much better than that. And of course, like we have a great toolbox, and we call that constraint-based modeling techniques. And so let's switch to modeling microbial communities. Usually we can see it in two types of models that people use. Basically, the goal is to describe and predict community metabolism using genome scale metabolic models. The good thing is that it really gives more biochemical details, and you can know what the exact, not exact, but have suggest some possibilities of what biochemical production is more likely through which biochemical pathway. And a superorganism model refers to like treating a whole microbiome or community as one single organism, and you merge all reactions in one big compartment and then try to just simulate things similar to the flux balance analysis. And then a more detailed level or individual level is a multi-organism model, where you have model compartmentalized by different taxa or representative species, and you can use representative genomes, or more recently people start to use a lot what we call MAGs, metagenome assembled genomes, to do such modeling. Initially people do this kind of multi-organism model using a direct extension of FBA. I like to call that joint FBA. Basically, the organisms are compartmentalized into different organisms, of course, but then they are still optimized under one single objective function. You still have those intracellular steady state, and then you also have additional constraint to control or to model the community exchange. Usually we just maximize the sum of all biomass production rate, and in this sense it's pretty much similar to like a multicellular model for like for eukaryotic organisms, or multi-compartment model. You still maximize it, optimize it with respect to only one objective function. And like initially I done some work using this, for example, to test some hypothesis that our collaborator at that time suspected. Like he actually tried to put a drug in some mouse and then see some change in the microbial communities, and he suspect the reason is like is the biosalt hydrolase activity, which from the literature at that time was supposed to be proportional to Clostridium and Lactobacillus, and that activity changed for example, the SCFA productions and other amino acids consumption. And we can test hypotheses like that, and by constraining the experimental data and look at, for example, the FBA range of different productions, and see, oh, with that, if I really assume that and further assume some community inhibition by that drug is applied, and then we really see some correlation in the predicted profile of SCFAs and amino acids with experimental data. So and one suggestion based on the modeling was the taurine released by biosalt hydrolase that becomes additional carbon source and nitrogen source for the microbes. So stimulating more this succinate fatty acid production. So I just want to go through that quickly. And but then yeah, of course we see issues of this joint FBA framework. It just maximizes the sum of all biomass production under one single objective function, and I like to call this a false altruism. You can see on the right diagram here, it's like yeah, the top cells is like the yes man. So because the other cells say, oh, I'm more efficient in using the resource, so why not you just share everything with me, and then the whole community will have a higher biomass because I produce biomass more efficiently. So let's share, and then the top cell just said yes, and I will share with you. And if you simulate a scenario like that, it would just say, oh, the other cells just grow extremely well, but the top cell is not growing at all. And this is some unrealistic cross-fitting that we can expect from joint FBA. And the next thing I did was to try to mitigate that by which partially only by imposing that equal specific growth rate for all community members. which is a consequence of the steady state composition that I implement. So the idea is if the community you're modeling is stable enough, then the composition you should have at least like an average steady state composition. And if you just simply assume exponential growth like on here, just an exponential growth with a constant depth rate, and this is the relative abundance, and you can derive the replicator equation where the change in relative abundance will be proportional to this, and the consequence of a steady state of this is that everything will grow in the same specific rate. So this is where we have that steady com earlier. Assume an average equal growth rate of organisms in the communities, and yeah, it shows some improvement when I apply that to gut community, 9 species, and it seems to predict the a more realistic microbiome composition, at least at the higher level, higher taxonomic level. Like we predict like dominance by Bacteroides and Firmicutes, and but still predict some not low but non-zero actinobacteria and proteobacteria. But if you just simply do the joint FBA, it's basically will over predict the bacilli in there, because they just has a high growth yield in rich media. And also interesting things that that it can do is to like do some sensitivity analysis and see how the diet would impact the interactions and suction fatty acid productions. I won't go too much about that, and that's the map formulation of that steady com. Basically implement this constant growth rate and with some proper scaling of fluxes. And the good thing about this framework was that it was able to it is compatible with FBA, so you can do flux variability analysis pretty easily with this framework. So and the other way, usual way of people modeling microbial communities is to do dynamic FBA. I guess most of you are also pretty familiar with that. So in contrast to joint FBA, here you in turn you maximize the biomass of individual organism, and then you iteratively update the extracellular environment based on the flux, and then you iteratively solve the FBA embedded differential equations. So basically, you have a solve the FBA problem each time step given the environmental conditions, which will change your uptake conditions or uptake bounds in your FBA problem, and then you use that to update the population and I mean the biomass as well as the concentrations of metabolized environment, and iteratively, and then you can simulate things. So one of my other work was to try to like incorporate a steady com as a steady state with dynamic flux balance analysis to try to model the gut environment, like where we dissect the community near the mucus layer and those in the lumen into 2 communities. And for those on the mucus layer, we assume they're close to a more steady, stable community. And then in the lumen, we assume they're like dynamically changing, like as the food pass through intestine, and you know what that becomes at the end, right? The microbes just accumulate in there and do some metabolism in there, and try to simulate things, and it works pretty well to capture like the ratio of facultative anaerobes and aerobes versus like strict anaerobes, and can sort of qualitatively simulate the accumulation of luminal biomass there, and that's pretty interesting. And we've found that like the oxygen to biomass ratio on the mucus layer, like the most important factor that shape how this aerobes versus anaerobes organize spatially. Okay, so but we still see some issues with the dynamic FBA. Now they they seem selfish enough that you optimize each individual objective function. But then one thing I was concerned is that they have no way to sense and respond to the metabolic potential of other organisms. Like they don't know what others might be able to do and act correspondingly. And this is like the very end of the false altruism. It's like they have no way to develop that that mutualism if you don't hard code it in your model. If you don't like add a constraint to force that to secrete something, then they probably will not do that, because they only sense things in the environment. But you know, in the natural communities, maybe they are adapted or selected to have some sort of mutualistic interactions that might not be able to predict by the FBA. So and two motivating examples that can capture the like the dynamic in this modeling is like the on top one. Let's say we have two species. One is they both can synthesize the two biomass precursor A and B, but one have a better efficiency at synthesizing B, the other better efficiency synthesizing A. So like, should they share the resource to maximize their yield? And in this case, yeah, that's the question. Should they crossfeed each other? It seems like crossfeeding each other might be a better option for both of them. But at the same time, like if they behave selfishly, then maybe they shouldn't crossfeed each other. And how about we go to more extreme? So now it becomes like an auxotrophic community. So like one auxotrophic for one precursor, then what will happen? So and we see that they're a good test case based on some evolutionary game theory consideration to test like the joint FBA and DFBA, as well as like a recent framework that we proposed called an NECOM. So evolution game theory is just game theory applied to ecology, and like although you can say many organisms don't really know how to choose, but natural selection's adaptation should determine what strategies will thrive in the nature. And the Nash equilibrium is just a state where no player can do better by unilaterally changing its own strategy. So this is the map definition, and this is a very conventional, or like the classical prisoner dynamic game, where you can see like, although if they both, like two prisoners get caught by police, if they both remain silent, then it seems like they will get the least penalty. But then because if one of them confess, then it can go free, but the other guy will suffer more. But then both of them will see that both of them will see that switching the strategy actually maximize their own benefits at that point. So eventually both of them will switch to this confession point, and both of them confession is the only Nash equilibrium here, which is sad, but true thing in many life situations maybe. So if you look at this example one, you'll find that it's actually a prisoner dynamics. If we do some FBA simulations, we actually find that even if you start at this most mutualistic scenarios where all of them secreting A and B both, but you see that like for the species 2 here, this organism, if it reduces secretion, then it actually have more resource to produce more biomass. So it probably will switch. So evolutionary game theory say like it probably switch. And then at this point, the species 1 will say, I can also reduce my secretion and increase my production of biomass. So I have a higher reproductive success. And this will happen iteratively until none of them are secreting things. So yeah, they become indifferent to what the others do. They just do their own thing. But if you look at the motivating example 2, like if they become autotrophic, then in this case, actually, like it doesn't really have an incentive to switch, given that the limiting reactant is the one that is secreted by the other organism. So even if you reduce your own secretion, you don't really get a lot of benefits. So you don't really have the incentive to switch for both of them. And in this case, actually, every strategy here, secreting or not, a weak Nash equilibrium, because actually what you do, you're already maximizing your own benefits, but you cannot change that because it depends on the action of the other guys. So all of them are weak Nash equilibrium, but then if you choose to cooperate, so you have a higher fitness. So the mutualistic phenotype should still be at least stable, locally stable. So, and how to find Nash equilibrium in general, especially when we're talking about in this metabolic model context. So one previous work by Samaroidi, Ali Samaroidi, also he's a former, also previously in Costas Marino's lab, and he tried to build payoff matrices like the matrix, like in matrix game, but do that using FBA to simulate each the fitness of each scenario, and then simulate the replicator dynamics based on that replicator equations you've seen earlier. But then one thing is that it need to predefine some metabolic strategy. Say I will test if it produce this or not, and then let them compete together in a framework similar to the FBA. But then the problem is that microbial metabolic interactions, actually the strategy space is not a very simple matrix game, because you know the feasible flux space is convex polytope, where and the thing is, whenever someone changes their strategy, it's also change the space of the other guys. So if I choose to not secrete that one, then you don't have the chance to take that strategy. So it's not simple matrix game. And what we propose is to modify the previous opcom. It's similar to that, but the details are a little different, and we call that anycom. And basically, we're in a problem, we still maximize each owns fitness function, which is also the growth rate. And but the thing is that we model that such that you don't have false altruism, like we don't actually have outer variables here, or the upper level variables here. It cannot force the individual to produce something that is against its own benefit. But at the same time, because you put it in a bilevel framework, it has the possibility to detect some solutions that can benefit each other while they're not forced to be altruistic. So yeah, that's the actual map framework, and we add a max function here so that the uptake and secretion or the uptake is bounded by the availability of other metabolites, while at the same time it doesn't impose a forced production of some metabolites. Okay, and then we see that when we run that, like the first example, the anycom framework can really capture that, same as the DFBA framework, capture the more non-cooperative behavior here, because each of them can sustain themselves. But like you can see, the joint FBA and even Opcom will predict that they will cross-feed each other, which is not a Nash equilibrium based on traditional game analysis. And example 2, we see that DFBA would only be able to predict the non-cooperating case, which is not growing at all. But anycom can also predict. Actually, every point here would become a feasible solution. But then, if we use the outer objective function to find something that has a higher overall growth rate, which is closer to, which should be easier to be a stable solution, but it's still not satisfy any like former formal stability requirement. Then it actually captured that mutualistic solution there. And we also tested like this scenario that you see earlier. So if I really have one guy the host, and this is, I call this a parasite that depends the secretion of the host, but it can produce biomass more efficiently. Like, would the host still only secrete to the parasite without caring about its own growth? And we see that Anycom does not force that behavior on the host, so the host can still grow. And this is regardless of whether we impose that the cumulative objective function or the outer level objective function. Even we don't impose that, it still predict that as the only feasible solution, because the host have to maintain its own fitness, the optimal fitness. But we see that like the joint FBA and the outcome will all predict like secrete something to the parasites. And we also analyze this exoenzyme production, which early Jeff Gore's group has analyzed this using also evolutionary game theory, which is just because that's a very interesting topic in ecology. Like whenever you want to secrete some bulk polymer, in this case only sucrose, actually, you need to secrete some exoenzyme to degrade them and then take it up into your cells to metabolize the monomers. But the thing is, someone can always cheat to not secrete them and gain some benefits. And we also tested that in a metabolic context, and we do see the same trend where if the cost of secreting is less than the benefit it can get, then it will converge to some cooperative scenario where they will all secrete and contribute. But if the cost is equal to benefit, then is like secreting or not, they can both exist, like the cheater and the contributors and the cooperators. But if the cost is really bigger than the benefits, then like no one would choose to cooperate, because it doesn't does any good. So, and after all this, we can say, oh, whether they really describe some real system, and it's really hard to find like experimental data that detailed enough that you can predict them. But we applied this to one previous co-culture experiments, pretty large scale, a lot of conditions, which is a cumulative of Saccharomyces cerevisiae, yeast, and some algae, where they're supposed to be mutualistic. One take up glucose and produce some CO2, while the other like will convert some nitrites and produce and feed the Saccharomyces with some ammonium. So and we analyze all the data point there and infer some uptake rates based on the experimental data, and then use those as input to like both Anycom and joint FBA for the cumulative model. And then we see that actually Anycom will predict overall, if summing all the data point, it predict a lot less error, more accurately, I'll say. And we can see that joint FBA in most of the time over predict the growth of the algae there. And the reason is because I think the yeast has a better growth yield if you just look at the medium there. So when you run joint FBA, again, it forces the algae to just secrete as much metabolize as it can to the yeast, so that the overall cumulative growth rate is higher. But if you run Anycom, it show a more realistic results that you don't see you don't see them exchanging everything, but some important metabolites. So yeah, I'm still in time. So the summary is to just basically FBA and DFBA important and fundamental frameworks for predicting microbial metabolism. But when we apply them to microbial communities, we see some insufficiencies, and really we need to integrate new principles and new algorithms to improve them. And the artifact of FBA as a single objective, single level optimization problems is that false altruism we discussed today. And we talk about how to incorporate steady state composition and some Nash equilibrium to try to mitigate that. But still, I'll say there are a lot of challenges ahead because and you see like bilevel framework is not easy to solve, and whenever it gets to dynamic environment is way more difficult and hard to model, and especially how you really define strategies and phenotype in a dynamic environment is really an open question, I would say. So that's all I want to share today. Thanks my president who did this work.
So thank you very much, Joshua, for your fantastic talk.